Our screencast today is focusing on acid-base equilibria problems. This comes out of chapter 16 in your textbook. So this section is titled pH Calculations and Equilibrium. A couple of important things to remember is don't try to just memorize one method to approach these problems. Of course, you always want to make sure your equation is balanced and you want to write your equilibrium expression. You want to think the problem through. That's the big thing. Think about what's going on. If it's a strong acid or a strong base, we know that it's going to dissociate 100%. So virtually at the point that this process is completed, there's zero of the original acid molecule or the base molecule present. So we assume 100% dissociation if it's a strong acid or a strong base. Now remember, the strong acids, there's only 6 strong acids, and that's your 6-pack of acids. Hydrochloric, hydrobromic, hydroiodic, perchloric acid, sulfuric acid, and nitric acid. You want to determine which components are significant and which ones can be ignored. And that is determined basically by if it's a strong acid or strong base, we can ignore the reactants. It's completely dissociating. If it's a weak acid or weak base, we'll talk about that in a different video lesson. Then you're going to treat it as an equilibrium problem and apply some of the methods we've learned about prior to in chapter 15. So let's also think about dissociation of a strong base. So this is a general reaction for a base, strong base. Remember, your strong bases are metallic hydroxides, specifically group 1A and 2A metal hydroxides. So here I just have an M for metal with the OH. It's going to dissociate. Again, we're going to assume 100% dissociation. So all of it shifts and you produce completely a set of ions in solution. The group 2A hydroxides, calcium, barium, magnesium, and strontium, are less soluble, but we still assume 100% dissociation with these. So the pH of strong bases is calculated directly from the concentration of the base in solution. So let's look at example 1. So when you look at this problem, look at the question, you see that the molecule in question is hydrochloric acid, which is a strong acid. So we're going to assume 100% dissociation. So let's first write our chemical equation. Now for this first example, I am going to ice the problem using some of the strategies we talked about in chapter 15. But since this is a strong acid, I am going to assume 100% dissociation. This will dissociate into the hydrogen ion and the chloride ion. So let's again look at icing our problem. I, remember, stands for your initial concentrations. The C stands for the change that occurs in order to reach equilibrium or for the reaction to occur. And E stands for your equilibrium concentrations. So this is telling you it's a 1.0 molar hydrochloric acid solution. So of course we know water is present because these are aqueous. Ions are aqueous. You don't have to write these in here, just understand that they are aqueous. So 1.0 molar, and initially we have none of the products present. Since this is a strong acid, it's going to dissociate 100%. So instead of defining our change or our shift in terms of X, we know all of it is going to be used up. So minus 1.0 molar for the HCl. The products are going to form so that we get pluses here. So plus 1.0 plus 1.0. So that means at equilibrium, as I said earlier, there's virtually zero of the original acid present because this is a strong acid. And we have 1.0 molar of the hydrogen ion and 1.0 molar of the chloride ion present. Now keep in mind, what they're asking us to find is the pH. So remember The formula for calculating pH is pH is equal to negative log of the hydrogen ion concentration. Again, make sure you show your work as you work through these problems. If this were a quiz or a test, I would expect to see the work that I'm showing here. So pH is equal to negative log of the hydrogen ion. Now look right here. This is our hydrogen ion concentration at equilibrium, which it really doesn't form equilibrium, but we're assuming, because we're assuming strong acids and strong bases dissociate 100%. So negative log of 1.0 is going to be what we plug into our calculator. And remember the rules for sig figs, when using logs, the number of sig figs in your concentration here is going to equal to the number of decimal places in your pH. So you get 0 for your answer, but we need 2 decimal places because we had 2 sig figs here. So the pH is equal to 0.00. All right, let's look at example 2. Now here we have sodium hydroxide, and it wants us to find the pH of a 1.8 times 10 to the negative 4 molar sodium hydroxide solution. So I'm going to write the equation. I would expect to see this. You do not have to write the 100% here, but just to remind you, it is going to dissociate 100% into the sodium ion and to the hydroxide ion. Notice it's a 1-to-1-to-1 ratio. That's important to pay attention to for these problems. We're going to ice the problem. Remember, initially, there's none of the product present, so we know it's going to shift to the products, but we do have 1.8 times 10 to the negative 4 molar of the sodium hydroxide initially. Since this is a strong base, we're going to say minus, plus, plus, and all of it's going to be consumed. So minus 1.8 times 10 to the negative 4 leaves me with none of the original base. But here I'm going to end up with 1.8 times 10 to the negative 4 of the sodium ion, as well as 1.8 times 10 to the negative 4 molar of the hydroxide ion. Now this is the ion that's important to focus on here. We are looking for the pH, but we have the OH concentration. Now recall that pOH can be calculated by taking the negative log of the OH concentration. So now that we know the hydroxide ion concentration, we can find the pOH and then from there find the pH. So negative log of 1.8 times 10 to the negative 4, and that will give us a pOH of 3.74. Now remember, the number of sig figs in your concentration are going to equal to the number of decimal places in your pH or your pOH. All right, now we're not quite finished because they wanted the pH. Now remember, we know that the pH plus the pOH always adds up to that pH scale 14, and that's an unlimited sig fig number, just to remind you of that. So the pH is going to be equal to 14 minus the pOH, so 14 minus 3.74. Now, since the 14 has unlimited decimal places and the pOH has 2 decimal places, we're going to round our pH to 2 decimal places as well. So that's going to give us a pH of 10.26. So this will definitely be a basic solution because the pH is greater than 7, and we would expect that because this is a strong base. Example 3. Here we have another base because it's a metal hydroxide. So let's write our equation. MgOH2. Now this is going to dissociate 100% into the magnesium ion. Now remember, he has a 2+ charge. And now be careful here. 2 hydroxide ions form because of the 2 here. This is a 1-to-1-to-2 ratio. This is still wanting us to calculate the pH in the end. We're going to use some of the same strategies. We're going to ice our problem. 1.0 times 10 to the negative 5 molar is the original concentration of the base, and 0.0 for the 2 ions initially. But when this shifts, since it's a strong base, it's minus 1.0 times 10 to the negative 5 and plus 1.0 times 10 to the negative 5. Now be careful here. This